this, we're going to look at rates of reaction, or reaction rates. And there's kind of two things that help us to determine reaction rates. The first is simply just a rule of thumb, and the rule of thumb is that for every 10-degree temperature rise, so every 10-degree change in temperature, if we raise it, we double our rate. And obviously, if we lower it by 10 degrees, we're going to halve our rate. So here is just an example. At 35 degrees Celsius, a certain reaction is able to produce 2.4 moles of product per minute. At what rate might the product be produced at 25 degrees Celsius, if we just use our rule of thumb up here? Is it always true? No, but it's approximately true with many reactions. So we are decreasing our temperature by 10 degrees. This is what should happen to our rate. Our molecules are moving less quick, so our rate should go down, and it should be halved. So if our initial rate is 2.4 moles per second, if we drop our temperature by 10 degrees, we might expect a rate of 1.20 moles per second. Alright? And if we look at the second example, at what rate might the product be produced at 65 degrees Celsius? Alright? So 65 is 30 degrees higher than 35 degrees. So we need to double 2.4 3 times. So we have 2.4 times 2, that's 10 degrees, times another 2, that's 20 degrees, times another 2, that would be 30 degrees, which is what our temperature change is. So 2.4 times 2 times 2 times 2, so 2.4 times is 4.8, times 2 is 9.6, times 2 would be 19.2 moles per second. Alright, so just rule of thumb, for every 10-degree temperature change, our rate doubles. The other thing that you need to know is that rates are stoichiometrically dependent. So a long time ago, we talked about stoichiometry. And in stoichiometry, really the only thing that we are concerned about is our coefficients, or are our coefficients. So in this balanced equation, it's already balanced for us. We have a 2 to 5 to 2 to 6 ratio. Alright, and that becomes very important in determining rates. So down here, we have if the initial, or that should be initial rate, of the reaction consumes 4 moles of methane per second, what is the rate at which oxygen is consumed initially? So with this equation, we can set it up like fence and rail if you'd like. So we might just do 4 moles of methane, which is CH4, and then just do a quick fence and rail problem. So in our balanced equation, we have no methane. We actually have ethane, so I'm just going to cross through this M right here and pretend that did not exist. Alright, so we have ethane, C2H6, and we have 2 moles of C2H6. So we're going to change that to ethane. And we want to find out how much oxygen is consumed initially. So this is simply a 2 to 5 mole ratio. So 5 moles of O2. So if we take 4 times 5, that's 20 divided by 2, we should have 10 moles per second. Alright? Similarly, in the second example, if the initial rate of the reaction consumes 2.5 moles of oxygen per second, we want to know what is the rate at which carbon dioxide is formed initially. So oxygen, our coefficient is 5 moles of oxygen. And we want to know carbon dioxide, which is at 2. So 2.5 times 2 is 5, divided by 5 is simply 1 mole per second. Alright? So again, rates are stoichiometrically dependent. Stoichiometry depends on coefficients in the balanced equation, and it's simply a short fence and rail problem, and that is how you can determine, if you know the rate of one reactant or product, you can always determine the rate of any other reactant or product, because their rates depend on coefficients.